are there any questions now, and it's particularly about the stuff from that I've been doing up until now, or about what I'm trying to do in the next few classes? No. Okay, so if there's no questions for now, let me go back. Let's go. I'll try to and explain where we are. So last time, let me see, how do I want to say this? Okay. So what this is all about is what's called Phasespace. And I'll write it often when I write M in this part of the class, I'm generally talking about this Phasespace, and it's going to be so this is actually kind of a general notion that and this I'll say some more about the geometry next time, about what you can actually have a curved Phasespace, or you can more abstractly think about the Phasespace as being the space of solutions of some equation of motion in general. But it's going to be, for us now, it's important that it's always going to be just a linear space, R2D, and then with coordinates, some Q1 to QD and P1 to PD. So we're not going to use this interpretation now, but these have here's a physical interpretation that this Phasespace is the positions and momenta of some some system of particles, or some system of degrees of freedom at a given time zero, and then you're going to evolve from that. You're going to try to understand how they evolve in later times. But this interpretation as of these are the positions and these are the momenta isn't really it is not something we're going to need right now. We're going to work in kind of much more abstractly about this. Okay. Let's see. Now okay. So now on functions so what I tried to explain last time is on functions on n. On M, you have this thing called a Poisson bracket, which I'll write this way. So you put it. So this is something that you feed it to. I won't write down the formula again, the standard formula I wrote down last time, but you feed it a function here, and you do some computation, and you get a third function. And so but the properties of this. So this is a new bracket on the infinite-dimensional space of functions of M, and generally also to try to keep things simple. The functions on M I'm going to be thinking about are pretty much always going to be just polynomial functions on so mostly be polynomial functions on N on M. And so it turns so the functions, it makes these functions of the algebra infinite dimensional algebra. Because it turns out that this guy is the anti-symmetry property of a Lie bracket. He also has the satisfies the Jacobi identity. So you have an infinite dimensional vector space, which is all functions on R2n, on R2d, or which you can think of as being all polynomial functions, and this Lie bracket turns this into a Lie algebra, but it's as a vector space, it's infinite dimensional. So it's not something that you can write down in terms of matrices or anything like that. Okay, and then now inside. Okay, so now what we're going to do is we're going to actually. here it's going to be crucial to us. So it's crucial for us that you know, M is linear. So that I mean, in general, this is all going to be true for, you know, for you know, arbitrary spaces M. You can define functions on, anyway, it's possible to define a Poisson bracket on much more general kinds of manifolds, but we're going to just use the fact that this is actually a linear space, and that we want because we need. So we're going to be thinking a lot about the dual space, about the space, which is the space of linear functions on here, and this dual space. It's also R2D, but it only kind of makes sense if you start with a linear space. Okay, but now on this okay, so then you have that the QJ, J, P, J are basis. So you can think of these coordinates, these Q and P coordinates, as being as being basis. They're the basis elements of the dual space of R2D. It's always true for, you know, linear coordinates on a linear space. And then what you do is then you have. So if you just start thinking about what does the Poisson bracket do just on these on these linear functions, you have, you know, Q, J, PK is equal to delta JK times just 1 times the function 1, and you have these guys. So you have these basic relations from these you can calculate what the Poisson bracket. So these give you on any linear function, on any, let me see. So in other words, so if you have some kind of linear combination of these p's and if you have some kind of linear combination of some linear function, is just going to be a linear combination of the q's and p's. And if you and knowing these relations, you can calculate this on any element and stuff. And so and sometimes I'm going to use notation. Sometimes when I say omega is this on, okay, so I mean, sometimes I want to just restrict, instead of thinking about the Poisson bracket on any function, I just want to think about what's the Poisson bracket doing on these linear combinations of q's and p's. And so it's now becomes a bilinear form on the dual space to M, and I'll call that bilinear form omega sometimes. But all I really need when I write down omega is I really need to be the Poisson bracket, and we're just using it on the linear function. Okay. Okay, so this is the setup, and now okay. Let's see what I want to. Yeah. Okay. So the first thing to say about this, oh boy. Okay, so the first, one thing to say about this is that the M star. So these are the things that are linear combinations of P's and Q's, and if you put together, just remember, so these are constant functions. Functions on M is a subly algebra. Of dimension 2D plus 1, and it's isomorphic to the Heisenberg algebra. Okay. So if you just, instead of thinking about all functions, if you just think about linear functions and including the constants, then you've got you have a subly algebra, because you can see that if you're taking Lie brackets of any such things gives you another such thing, and it's the Lie algebra we already talked about, which is the Heisenberg Lie algebra. So you weirdly find what sounds like a quantum thing, the Heisenberg Lie algebra inside classical mechanics, just as the thing you get from linear functions. Okay, so now I want to do. So let me make an analogy. Okay, so I want to say a little bit about symplectic geometry today, and I'll say more about it next time. But here's the analogy. So recall, so in Euclidean geometry, so Euclidean geometry, you've got a vector space, which is called Rn. So, but there's more structure on the vector space. So this is based on having basis element. Vector J, let me just call it E. It is such that vector J in a bilinear form J, EK. So this is just the usual story about Euclidean geometry. It's you've got a vector space, and then you have a bilinear form on it, and this bilinear form is defined by what it does on an orthonormal basis, which is this. Oh, and then the crucial kind of thing about geometry here is that the group, you have O sub n. O of n is the group of linear transformations that preserve so then you look at whatever, if you just have a vector space, then you have a GLN. You can look at all linear transformations on it. If you put a bilinear form on it, that's non-degenerate like this, and like this, you can look at the subgroup of things that preserve it, and that's the orthogonal group. Okay, so this package is really what Euclidean geometry is about. And what we want to do today. Okay, so what I want to do today is notice that symplectic geometry. What you do is use you take your underlying vector space to be an even dimensional vector space. So Euclidean geometry works in any dimension, in odd dimensions, even dimensions. Symplectic geometry, you really need your vector space to be even dimensional. And then you use so then you consider what I called omega. Let me put it this way. Say it this way. So consider your basis elements Q, J, Pj that's satisfying the Poisson bracket relations. Okay, let me see what I wanted to say. Okay, let's just say consider yes, satisfying the Poisson bracket relation. Maybe let me just not say this. Say this, and then okay. Let's just say this. Let's consider these basis elements, and then we're going to consider a different bilinear form on this vector space, and then the bilinear form given by omega. Okay. And so if you write this out in coordinates, here you're going to have in coordinates this is going to be a matrix just 1 1 1 1 ones all the way down the diagonal and zeros elsewhere. If you write out this bilinear form as a matrix, here the fact that it's anti-symmetric and that it's anti-symmetric and it just matches QJ and PJ and gives you 1 and otherwise gives you 0. Here you're going to have the matrix is going to look more like block diagonal form 0 here, block diagonal the identity here, -1 here, and 0. So this is kind of you're going to have this guy. If you think of this guy right in as a matrix, in these with respect to this basis, you're going to have something that looks like this. And these are D by D. These are each D by D matrices. Okay. Okay. So this, in some sense, is what symplectic geometry is about. Now, the new thing, what we want to do is we want to define the analog. So we're interested in groups in the algebra. So we've been talking about these ON groups. And so what we want to do is we want to find the analog of the ON group for symplectic geometry. And it's going to be the, instead of being the group that preserves the bilinear form, it's going to be the group that preserves omega. So let me write that as a definition. Definition. I want to say it. So the symplectic group SP of QDR is the group of linear transformations preserving omega. Okay, so this is a so the Poisson bracket on, the Poisson bracket relations on these basis elements of these PJs and QJs gives you a bilinear form. You could have written it in terms of matrix the way I want it, or you could just look at what it does on the basis. And then you could ask, what are the linear transformations of this, now this 2D dimensional vector space that preserve, that don't change the values of this bilinear form. Okay, so now, so this is the definition. And let me do it this way. So what I'm going to do. So this is what we're going to be focusing on today. Is we're going to be focusing on trying to better understand this group and its Lie algebra. Okay. So now let's go. So instead of starting with a group, which I think I may have done more of in the book. Let me let's first see if we can get our hands. Let's first get our hands on the Lie algebra, because what's going to happen here is that the group is actually somewhat difficult to work with. There's anyway, you can we'll see how to work with it, but it's a little bit complicated. Again, it's a nonlinear object, but the Lie algebra is actually a much simpler thing to understand. And so I want to kind of tell you first tell you about the Lie algebra and see what we can do in the Lie algebra, and then get to the Lie group. Okay, but so the first thing to notice. So if you take the Lie bracket of a quadratic and another quadratic polynomial, and here what I'm saying quadratic, I really just mean order 2. I'm not including any lower order terms. Just so here I just mean a polynomial that all the terms are ordered 2. And if you take a polynomial of p's and q's where all the terms are ordered 2, and another one where all the terms are ordered 2, and you look at the formula for what happens when what happens to the degree of these polynomials when you take the 2 derivatives, what happens is that you're multiplying. Anyway, when if you do this with 2 of these things, two things of order 2 in the p's and each order 2 in the p's and q's, and look at the formula you get when you compute the Poisson bracket, you're going to get another one. And so what
homogeneous quadratic polynomials?
What?
So we mean homogeneous quadratic
homogeneous,
polynomials?
yeah.
Okay.
Yeah, that's maybe a better way to say it. I'm trying to avoid saying that everywhere. But yeah, so homogeneous, if you like. And then so now by the same kind of so what I'm the story I was telling you last time was, and at the beginning, was that you could understand the Heisenberg Lie algebra as the Lie algebra of kind of linear things, including the constants, and then you got a subalgebra. Here, this tells you that you get another subalgebra of this infinite dimensional Lie algebra of all functions on M. So this implies on the homogeneous quadratic polynomials on R2D on n is R2D are a Lie algebra. And it's just subalgebra of all polynomials. So, as I was saying, I mean, the problem with thinking about functions on the phase space as a Lie algebra is that it's an infinite dimensional one. But if you just look at these quadratic things, then you've actually got a finite dimensional thing. You can figure out what the dimension of this thing is. Okay, and let's see what I want to do. Okay. And so what we're going to do is and we'll see, and part of the point of all these computations in this chapter 16 are to kind of just to show, we'll show this is, or this is what I mean in this chapter 16 that these are, this is the Lie algebra of SP. So this is what I mean by saying that the symplectic group may be, it's not a nonlinear group of 2D by 2D matrix. It's a group of 2D by 2D matrices. It's satisfying a certain condition. It's a little bit hard to work with to get your hands on, but it's actually very, very, very easy to do computations and to get your hands on its Lie algebra, because its Lie algebra is just going to be quadratic polynomials. And so, it turns out that if you start playing around with Poisson brackets and computing Poisson brackets, you quickly find that it's very easy to compute the Poisson bracket of two polynomials. You kind of repeatedly use the Leibniz rule to break everything to reduce the degree and then use the relations on the generators on the Q's and P's. So that's true. Okay. Okay, so this is one of the first things. Okay. So let me kind of stop with this. So this is just kind of first of all pointing out that you've now got your hands on a new finite dimensional Lie algebra, and the claim to be shown is to try to figure out what this guy has to do with this group, and it turns out he's the Lie algebra of that group. Okay. Now, let's see. Okay, so the next. So there's one more kind of interesting piece of the story about what happens when you start computing Poisson brackets on polynomials. You get so also notice. Let's see. That if you take that linear, and again, I'm always meaning homogeneous. So homogeneous linear. If you Poisson bracket them with a quadratic. Okay, what you get is something homogeneous linear. If you put together something that's order 1 in the P's and Q's and take a Poisson bracket with something that's order 2 in the P's and Q's, you get something that's order 1 in the P's and Q's. And again, it's just from the way the formula works out. Okay, so this is interesting. So there's later on there's something which is in the section 16.2 is that you have a quite interesting structure here, because you've got these guys together with the constants are giving you a Lie subalgebra. These guys are giving you a Lie subalgebra, And then you've got interesting Lie algebra relations between these two Lies of algebras. So I'll say more about this at some point, maybe next time. But the point is that you can, you can actually put together, really the truly quadratic things, the things which are all the things which are of order 2, not homogeneous, and those are going to give you some bigger Lies of algebra, and it's going to include the Heisenberg stuff and the symplectic stuff, and this is telling you something interesting about the relations between the symplectic stuff and the Heisenberg stuff. But we'll get to that later, not right now. Okay, so now what I'm going to do, so the plan, when I initially wrote this down, what's in chapter 5, is that I'm trying to use to say some things about this by using geometry, by using the kind of geometrical interpretation of what you're doing here. But turns out you don't actually need, you need very, very little of this. And maybe one way just to say what you actually, you only kind of really need kind of one main piece of information about this, which is this, which is this basic principle, which you have in Hamiltonian mechanics. That is that if recall that if h is the Hamiltonian function, then time evolution, then evolution, which you can think of as translation in time. So there's a real translation group which you can think of as time translation, is given by acts on functions on M. EFD. Okay, so this is Hamilton's basic equation, and if you write this, so this is the thing which tells you, if you got any kind of observable f, which is some function of the p's and q's, how are the values of this observable going to change as you translate along as you translate in time along solutions to the equations of motion. And if you write these equations down for f is just for the generators, for f is p and f is q, then you just get the standard version of kind of Hamilton's equations that I wrote down earlier. So this is really just the general version. This is just Hamilton's equation. But what I want to kind of use this thing to do is to give. So I want to use this to give some kind of interpretation to all these calculations that I'm doing involving these Poisson brackets. So the idea is so we'll want to think to use this to think about what Poisson bracket with h is homogeneous quadratic. So we want to think these various Poisson brackets that we've been using. If you want to think of them as being, you want to take this guy. So you want to take this guy to think about what happens if this guy is just a quadratic polynomial. And then you're gonna, anyway, and then we're gonna, and then one way of thinking about kind of what the, is, so this is, so H is then the infinitesimal generator of time translation. Okay. So the general principle that we're interested in here is going to be that we want to, if we know that our system has some kind of symmetry, what we want to do is we want to find the corresponding function which generates that symmetry, in the same sense that this H generates, you know, motion along time translation along trajectories. Well, if you pick some other quadratic polynomial and look at what it's doing, it's you know, it's telling you, you know, how it's giving you the infinitesimal action at t is equal to 0 by this derivative of some kind of some kind of transformation of the whole system of any of the other functions. And I don't want to say more about it. And what I was trying to do in this chapter 15 was to kind of explain the relationship of that to geometry. But I'll say more about that next time. But this is just kind of one way to get your hand on, you know, get your hands on what we're actually, what's the actual significance of some of these quadratic functions. And you'll see that, you know, continually both physicists and mathematicians will refer to something as the function which generates a symmetry. Well, this is really what this means. That we're going to think of these functions as being as the things which kind of give some kind of, it's like we've got one element of a Lie algebra, and we're figuring out, you know, what happens if you kind of exponentiate the action of that Lie algebra element on the whole and have a group action of the whole system, that you're going to get something like this. But I'll say more about that point of view next time. Okay, so that's a bit vague, but let me let me now do this. So this is more some kind of motivation for what I want to do. So. Okay, so now, if you think again about this guy, that what this is telling you is that so if H is you know, again, homogeneous quadratic polynomial, then an F homogeneous linear. Well, let me just say it this way: F element dual. Then df, then, you know, F with H is going to be is also going to be okay. So what these so if you think of these quadratic functions, or these homogeneous quadratic polynomials, if you think of these things as generators of some kind of action, where you're gonna move along in some way parameterized by t, then what they do to linear functions is the infinitesimal change of a linear function is another linear function. And so this implies that f of t, that if f of 0 is an element of m star, so is f of t. So what these things do, so what these h's do is they give a so h gives an an action. Anyway, so what h is going to give you is it basically gives you a for each t a linear transformation on m star, right? And then and then the derivative, and then ddt at t is equal to 0 is given is bracket with h. Okay. So anyway, so this is the structure that you're getting at this thing, and so these things are really telling you about, anyway, they're giving you kind of infinitesimal linear transformations of this vector space. Okay. Yeah.
To impose the condition that we're evaluating the derivative at t equals 0, so
Yeah.
Is the Poisson bracket with the Hamiltonian also evaluated at t equals 0 then?
So this is true. Yeah. So actually, it's a little bit confusing. When I write down this function, I guess I'm using. When I write down this equation, I'm. I guess this is where I get into the confusing aspect of the geometry. That h is always constant, so I'm going to be thinking about constant Hamiltonians that don't change in time. But this f can change in time. Okay, does that help? And it's just saying, yeah. And so I want to solve this equation in general. It's going to be true for all t, but in particular, it's also going to be true at t is equal to 0, right? Does that make sense? Yeah.
So I'm asking, like, for the last equation you wrote, like, just looking at the operator, the derivative.
Yeah.
Evaluated at time equals 0. So, like,
yeah.
On the right hand side, then.
Yeah.
So without the condition that we're evaluating at time equals 0, then it's just bracket with h as you wrote.
Yeah, I guess all I'm doing is saying here is just restating this condition at t is equal to 0. Yeah, so this is true for any. This is an equation I can try to solve for any t, and it's good. And you could. So this is a constant. This f changes with t, and but I'm just saying that the nature of the solution of this thing is going to be if you start off with some function that's a linear at 0, that's a linear function in here, then you're gonna have one at all later times, and it's going to be one that if you differentiate it at t is equal to 0, you're going to get this. So maybe I should say so ddt f of t. All I meant was that this is. Okay.
Okay, yeah.
Okay.
Makes sense.
Okay, good.
Oh, first I have a question.
Yeah.
About this. I cannot see why f is dependent on t, because f is the linear function on the phase space, right? And the phase space consists of only positions and momentum. Why is f a function of t?
Well, I guess it's a little bit confusing. When I wrote down Yeah, I mean the point is that when I write down this formula, I mean, I probably should have explained this better, but when you try and think about this formula, then you're going to have, yeah, I'm generalizing kind of the kind of t is equal to 0 story, where this is just a linear function, and this is a linear function. So I'm making this guy I'm making everything t dependent, except I don't want this guy to be t dependent. I want him to be t independent. Okay. So when I write down this equation implicitly, I've gone from thinking about but this is all, yeah, to looking at kind of linear. Yeah, well, I'm starting out by looking at functions of t in general, and then I'm showing that these are not just any functions of t. That if you start out with a linear function, a linear combination of these p's and q's, that you're gonna always have a linear combination of these p's and q's, as long as this guy is constant. Does that help?
Yeah.
Okay.
Oh.
Okay, and then the other thing to notice. So let me. Okay, so what's happening here is that this is giving me this h is kind of generating this for each it is giving me for each t a linear transformation on m star, and this kind of family of these linear transformations, its derivative at t is equal to 0 is given by just by this linear transformation, this linear map on f of 0. Okay, let me see. And then now so there's one more thing you can say about these linear maps, about the linear maps you're getting. And I hope I get this argument right. This may have this. So the claim. So notice, maybe say this. Notice that the evolution in t generated by h preserves omega. In other words, that so not only does, you know, if I solve that thing and get f of t, not only is that f of t. I hope I got this right. Okay, yeah, the ddt. Actually, maybe I should. Is this right? Yeah. And so what I mean by this is that given two of d f1 h and d f2 dt. I hope I've got this right. I may have this confuse myself with this thing. You have so you consider what the what f1 f2 is. Okay. So remember, all I've shown so far is that is that f1 and f2, as they move around, they remain linear. They remain in m star. They remain linear functions on m, but they also as a function of time and of t, and you have ddt. But this is still some function on phase space, depends upon time, and then I hope I've got this argument right. Let's see. Then you got f1, f2, h. But these guys, if you take the Poisson bracket of these two linear functions, you're going to get something which is not a linear function, but which is a constant depending on time. but this is but it's actually a constant depending on time. And then but now so then if you take so this is just some function of t, but if you bracket, you know, a function of t times, which is just the identity as a function of p and q with some quadratic function of p and q, you're going to get no, sorry, dt, sorry, dt, f1, f2, but this is equal to 0. So if I've got this argument right, then what I've shown is that there's something else that you can say about what this h does. This h kind of generates for each t a linear transformation of the space m star, but it's not just any linear transformation. It's a linear transformation which preserves the Poisson bracket, which preserves omega. So the idea is that this is so you get h generates linear transformations of m star preserving omega. So these are, you know, so at each t an element of the symplectic group. Okay. And this is kind of the fundamental reason why these h's are going to correspond to you know to the are going to be kind of to the Lie algebra elements, to the Lie algebra of the symplectic group. Okay. Let me see. I don't know if I want to, but again, I think let me to really explain this argument, to really see this argument better. Let me leave it for some more geometry next time, and just leave this as kind of a more of a motivation for what's going to happen next, because I think what I want to do now. Okay, so let me give one more kind of general story about where we're going, which I think will make, which is just extracting a piece of the story about the geometry from next time, and then I'll start working out some details for specific cases of this where you can actually compute things. Let me. So one more piece of kind of general structure. What we're doing is, so notice, so if, so here we go. So if Lie, so what we're gonna, what we're kind of, a very fundamental thing we're starting out with is that if G is any Lie group acting on M, you know, and thus star. Okay. So we've got some, you know, so we just got some. This is the very general situation we have when we're talking about. You've got some classical mechanical system, and we say that it has some kind of symmetry. So there's a Lie group acting on M, and since M is acting and you know linearly, so in some sense, so for each element of here in G, you're getting something in GL2D of R. And then if you have an action on M, you just have the dual action on dual space. So you have M such that G is P of QD R. So in other words, I mean that the action preserves omega. Then, okay. So this maybe it's a better. Okay, let me just say it this way. So this is the general situation. So this is really the general context we want to put ourselves in when we're talking about symmetries of classical mechanical systems. That you've got a group acting on the phase space, and to make this interesting, you need this the group action to preserve the Poisson brackets, or to preserve omega. Okay, and then you're going to have what's called a symplectic group action on this thing, and pretty much most of the cases we'll be interested in of symmetries are going to, in a classical context, correspond to this. But to get your hands on this and to do something really explicit, the thing to notice is that this implies that the Lie G, the subset of Lie P QD R. But what we want, but this guy, remember I told you, this guy is just going to be the quadratic this guy's going to be the quadratic polynomials, the actual quadratic polynomials. So what we want, so we want to identify, I'll write that for now, instead of using X, I'll write L as some element of Lie G. You want to find the corresponding quadratic function and call it the use of L. And so we want to find L, goes to use of L. And so here this is just and this is called this he goes to quadratic functions. So this thing is called the moment map. Okay, so this information can be packaged in various ways, but basically what we want is we want to think about the situation where we've got some arbitrary Lie algebra, some arbitrary Lie group acting on a phase space, and the only crucial thing is that this action preserve this bilinear form. So it's actually a symplectic action. So the group is sits somehow as a subgroup of the symplectic group, and so it means that its Lie algebra sits as a sub Lie algebra of the Lie algebra of these guys, and so we can get our hands on this group on what this group action is doing if we can actually identify for each element of the Lie algebra, we can identify the corresponding quadratic polynomial. So this is the main thing we're trying to do, and then to kind of get to get way ahead of ourselves. Then when we go to a quantum theory, quantization is then if we want to find the representation of a Lie group on a state space, we're going to start by finding the correct quadratic polynomial here, and then use and then quantize that in a sense. Okay, And then maybe just the example, which is the main which is kind of the main part of your problem set for Tuesday is the example. The example is going to be G is equal to SO3. And let me not write G is equal to SO3, acting on, acting by rotating, using Q vector and P vector. So if you take, if you do some kind of rotation of Q vectors, of your position vectors, and do the same rotation of your momentum vectors, that's going to give you an action of the rotation group on your phase space. Turns out you can check and see that action preserves the Poisson bracket. So that action is symplectic, and so SO3 sits inside SP. And now here you've got 3 of these and 3 of these, so it's 6R. And to each L sub j, the basis elements of the Lie algebra of SO3, you're going to get a quadratic function mu L sub j on R6. Okay. And so the problem is basically to try to identify this function, and the answer is going to be something that should be familiar from either a class on classical mechanics or quantum mechanics. It's the angular momentum function expressed in terms of q's and p's. So that's this is one of the kind of applications of this whole story that I've been telling you, and one example of it that you should try and work out for as part of the problem set next time. Okay, now let's start. Let me just kind of, so in this chapter 16, there's some I kind of worked out very in kind of gory detail and very specifically some what happens for examples. So let's go. So it's a good idea to think about what's happening first in. Anyway, so anyway, I worked out all the formulas for how all this works in coordinates. So first, it's a good idea to first think about d is equal to 1. And so this is all what's in the. I'm going to go through this fairly quickly because this is all just a bunch of long formulas that are written out in the section 16.1. And so what you want to do is so if you write. Okay, so writing elements of M are equal to R2 as C sub Q plus C sub P P. So in other words, I'm just writing this out with respect to this basis of the elements Q and P, and then omega of. Yeah. So omega is going to be something that you feed it to things like this. And let's write it. Let me just put the coefficients here: CQ, CP, and maybe and then some other one which is C prime Q, C prime P. If you use the Poisson bracket relations between two of these guys that way, then you find that the answer you get is CQ, CP prime minus CQ prime, and so which you could also, if you like, write as a. So you could write out this bilinear form. When I say writing out this bilinear form as a matrix, what I mean is writing this out in this form. That this is CQ, CP, 0, 1, minus 1, 0, CQ prime. Okay. So this is kind of what I meant by saying, that you could write this bilinear form as this matrix. And then you just want to do is you want to find linear transformations, alpha, beta, gamma, delta, that preserve this. And here, there's a calculation in the, anyway, so this calculation is done in the book. You can figure out if you multiply this guy by this and this guy by this, what's the condition that you don't change this guy. And so it's a condition that depends upon this matrix here. And you end up with it. This implies, and you get that the depth so you get that there's only one condition you need on these guys. So there's a real four-dimensional space of these, but then there's one real condition on these. So you get a three real dimensional subspace of these that preserves this, and it's just the one where the determinant is 1. So this is so this implies that SP, what I've shown by doing this, is that SP of 2R is something, is a group you've already heard about, which is SL2R. So in other words, it's the group of 2 by 2 linear transformations with determinant 1. Okay, and then the Lie, then you also know that that Lie algebra of SL2R is 2 by 2 proceeds with trace with 0 trace. The determinant 1 condition, if you anyway, having trace 0 is the condition that when you exponentiate, you get determinant 1. Okay. And then now what you want to do is get the relation to okay, and you can show. So let's see. So we have Lie SL2R is equal to 2 by 2 matrices, or polynomials. Or in other words, that I should, what's the, this guy is supposed to be quadratic polynomials. Anyway, this guy's supposed to be quadratic polynomials. Well, the Lie algebra, this guy's supposed to be quadratic polynomials, but this guy is just 2 by 2 matrices. So what's the identification? And I just want to, I work this out in the text that so that this guy, this basis element corresponds to q squared over 2. This basis element corresponds to minus p squared over 2, and then and then this guy 1 minus 1 0 0 corresponds to minus pq minus qp. Okay. So if you look at so the quadratic polynomials, homogeneous quadratic polynomials they're all linear combinations of q squared, p squared, and qp. Well, you can and they've got this Lie bracket relation between them that makes them a Lie algebra. Well, you can identify that with the Lie algebra of 2 by 2 real matrices that have trace 0, and there you have this guy, and this guy are a basis. And so if you identify these two bases, you get an isomorphism of Lie algebras. And so you can see anyway, so what I'm showing here, I guess, is that, you know, that this guy and this guy are the same thing. If you think of this guy's matrices, this guy's quadratic polynomials, then I'm showing this here. Okay, so then let me then just very quickly say what happens for in higher dimensions. Arbitrary D. Arbitrary D. What you do is let me write well, there's a fairly obvious notation that I'm just going to expand. So just take so use everything where I had constants and q's and p's. Just make everything vectors and use the dot product. So you're going to use CQ vector dot over the q vector plus CP vector dot over the p vector. So you're going to use this to be an arbitrary element of the dual. And then what you want to do is you how do I do this? Okay. And so you find, and then you use the Poisson bracket relations to show that that sp2r sp2dr is group of 2D by 2D matrices. These satisfying. You have to say that if you take 2D by 2D matrices G satisfying G, and then you take the transpose, and then you take the block diagonal thing. Okay, so these are everybody's a 2D by 2D matrix. So these are 2D by 2D block matrices. And so when I say that this group is a little bit hard to get your hands on, what I mean is that it's a group of 2D by 2D matrices satisfying this condition, which is a little bit hard to see. And then if you if you take that if G is equal to e to the TL. So if these group elements come by, and you have a condition that LT 0, 1, minus 1, 0, plus 0, 1, minus 1, 0, L is equal to 0. You basically plug this in here and differentiate with respect to T at T is equal to 0, and you get this condition on L. So the so this is the analog of the determinant 1 condition in the D is equal to 1 case. This is the analog of the trace-free condition in the D is equal to 1 case. But it's more complicated in higher dimensions. You have to do it this way. And then you find implies L, so that L has to have the block diagonal form of some D by D matrix.
So is there always an L corresponding to the G?
Is there always a what?
Is there always an L corresponding to the G?
Yeah. So these are actually I don't. Let me see. I'm not sure. Okay, and now these groups are tricky. They're non-compact. Yeah, and then so for instance, in SL2R, you're going to get So no, no. So this is only going to be true if G is close enough to the origin. You can also have, I think you can also have symplectic group matrices which don't. But yeah, so G. Anyway, yeah, there's some condition that you're only going to be able to solve this if you're close enough to the origin.
Okay, thank you.
A, B, C minus A, P transpose, and and that B and C are symmetric. Let's see. Okay, so I better stop here. It's getting late, but I mean, there's kind of what's worked out in the in this text is to show the idea is that you show that the condition to be in the Lie algebra that the Lie algebra of so L element of the Lie algebra of SP2D R, means that it has to be that you can write it in this as in terms of 2D by 2D matrices of this form. It's an arbitrary A D by D real matrix, another, and then it's minus this transpose here, and then two symmetric D by D matrices on the off diagonal part. And then the next part, which I won't write down then, is that you can then show, the next part is to find the corresponding quadratic polynomial. In other words, the use, what's the moment map here? That if I give you such a matrix, what you'd like to know, what you know is that you can, instead of thinking of this Lie algebra this way, you can think of it as a Lie algebra of quadratic polynomials, and so you then just want to know what's the quadratic polynomial corresponding to this matrix, and the formula is kind of is I think worked out in the text anyway. Okay, so I think I better stop this for now, and say that next week we'll start up. I'll kind of go backwards a little bit and explain, say a bit about the geometry, and that'll just to give some more context to these calculations, and it may be especially useful if you've seen if you already know some geometry, you may find it useful. Otherwise, you may find this context a bit confusing. But it's going to turn out that what we're going to do in the rest of the class, in terms of applications, in terms of going to the quantum theory and quantizing things, we actually only need the stuff that I've been talking about today. We don't actually need this general ideas about symplectic geometry, which are quite beautiful and quite useful in classical mechanics. They don't. The parts of it you need are really the parts I've talked about here, and a lot of it is because in quantum mechanics we're going to be interested in in producing observables corresponding to the Lie algebra of a symmetry, and so we really just need to understand very well what this Lie algebra looks like, and how to think of it in terms of quadratic polynomials. That's the main thing we're going to need in quantum theory. Okay, so any questions? No, anything for now? Okay, well, if not, we'll stop for now, and I'll either see you on next Tuesday, or definitely come back in a few minutes and we can talk about this or anything else. Okay. Okay. Bye now. Bye then.
Thank you. Bye.
Thank you.